We have our very own Kathy Mandt presenting on the origin of volatiles sampled by the LCROSS mission in Cabeus crater.
It's an honor to have the opportunity to share with you the research that we've been doing, re-looking at the measurements that were made by the LCROSS Impactor. Now, to provide some context to this research, I want to talk about how we use the moon as a cornerstone for understanding the history of the solar system. And as part of SURVEY and part of the lunar community, I think most of the people online understand and recognize how we have done this, in particular with the impact history of the moon. We have the impacts on the moon that the record has been preserved for billions of years, thanks to the moon not having an atmosphere and liquid water and life. And that helps us to understand the history of impacts to the moon. And then there are other implications for studying the moon for our understanding of the terrestrial planets and for, in general, the history of the solar system. As the Artemis mission program is ramping up and the CLIPS program as well, we are facing an unprecedented opportunity to start using the volatiles on the moon as a cornerstone for understanding the history of volatiles in delivery to the Earth-Moon system and the history of volatiles on the moon itself. And the Viper mission is the very important first step in this process. Now, we have been studying water on the moon for an extended period of time. We've been using remote sensing to confirm that water is present on the moon and to try and map it. And we understand that its distribution spatially is patchy and with depth can be patchy, but we still have so much to learn just about water. In addition to water, other volatiles are really important for helping us to understand what the origin of this water is and where it came from. Now, the one measurement that we've been able to achieve is through the LCROSS mission, where they impacted the Cabeus PSR, which is one of the coldest permanently shaded regions. And we're able to measure in the plume from that impact molecules that bear carbon, nitrogen, and sulfur. And the abundance of these molecules relative to water and their composition is very important for us to try and trace back to the sources. But how do we go about doing that? How do we take this measurement and look at the sources that could have provided the water and these other volatiles to the permanently shaded region and figure out what the most likely source is or the most likely mix of sources? This can be very complicated. I'm showing on the left what the possible sources could be. They're volcanic, cometary, asteroid, meteorite, and solar wind. 3 of these are impactors. Understanding them from molecular composition is extremely difficult. When volatiles are delivered to the moon, they have molecular composition, but that molecular composition can change significantly because of all this mess of processes that take place between delivery from the source and then long-term storage in the permanently shaded region. So and it's really difficult to figure out how many of these processes took place, what the rates were, how they impacted the molecular composition. In an attempt to get around this, what we have done is we've taken the molecular composition that was measured by LCROSS, both with the LCROSS mission and with the LAMP instrument on LRO, and looked at the elemental composition. So we're looking here at the carbon to sulfur ratio on the x-axis or on the y-axis and comparing that to the nitrogen to carbon, oxygen to carbon, and then carbon to hydrogen ratio. What we show in black is the LCROSS observations, and there's 2 interpretations of the LCROSS observations depending on how the ice was stored in the subsurface or in the regolith. Now, if these volatiles were stored in clath rates, which is water cages, what happens when the impact occurs is that the clath rates are destabilized and everything is just suddenly released into the plume. So we are interpreting the plume atmosphere as being, or the plume composition, if it's clath rates, as being representative of what's in the regolith. On the other hand, if the volatiles are just directly condensed onto the regolith grains, then their release is dependent on their volatility temperature. So Some volatiles are released more easily than others, and because of the heating of the regolith, more of the more volatile species would end up in the plume than water. So for example, carbon monoxide is more volatile. So what appears in the plume is actually more than would be in the regolith. So we have these two interpretations. Now you can see from this figure that no single source perfectly matches the measurements that were made in the LCROSS plume. So from this observation, or from this comparison here, you can't find a single source that without any fractionation of the element ratios would represent S. So what we have done is some modeling of what a mixture of sources of volatiles would be, what they would produce in the permanently shaded region and what would appear in the LCROSS plume based on a mixture of sources. With this model, we have taken 4 primary sources: volcanic, cometary, chondritic, and solar wind sources, and then looked at 167,000 possible mixtures of those sources. And then we looked at 5 different scenarios, starting with assuming that what was stored represents what was in the source and no fractionation. And from that, we found that no mixture of volatiles actually fits either. We looked at volcanic atmospheric processes, and that, based on what has recently been published by Tucker et al., for example, well, some people have been studying volcanic atmospheric processes. This is extremely complex and difficult to constrain. We looked at impact loss to space and class rate formation and sublimation and recondensation processes and how that would fractionate the element ratios. And what we found is that nitrogen and sulfur relative to carbon are really the key measurements for determining or ruling out potential sources for these volatiles. And the main conclusion that we found, because of the nitrogen to carbon ratio, is that it cannot be volcanic in origin. There's far too much nitrogen present in the volatiles to have a volcanic origin for the volatiles that were sampled by the LCROSS plume. And this is after a rigorous, detailed modeling of hundreds of thousands of models that we have run. What we have found is that the best result is a mixture of cometary ices and chondrites. Now, comets are a mixture of ice, they're icy dust balls. And the refractory material in comets is probably chondritic in nature. So the observations that were made by LCROSS could actually be explained by cometary sources because of a mixture of cometary ices and chondritic material. Now, in the future, as we start landing on the moon and studying these volatiles and making use of them for human exploration, it's very important to get in situ measurements, particularly of the D to H in water, and if possible, oxygen isotope ratios. We would also like nitrogen isotope ratios so that we can compare that with the known ratios of sources, and then sulfur isotope ratios are also very important. And with that, I will finish up. Is it time to move to the next speaker?
No, you're at exactly 8 minutes, in fact, so great job.
Okay.
Perfect timing. Yeah, so that
and we can make up time because we took up a little time with the introduction.
Yeah, well, let's see. Is there any questions in the chat? No. Well, I guess I'll ask a quick question. Clathrates on the moon. I haven't heard much about that. Any interesting things there to share?
Well, what we also found, because we took into account the way that class rate formation would influence the elemental ratios, we found that class rates are not a good explanation for the ices that were observed in the LCROSS plume. So we did not demonstrate that class rates exist on the moon. And I see in the chat, we have a question from Tom Orlando asking if we took into account the chemistry due to the impact. And we were able to kind of ignore that because we're not looking at molecular composition and we're assuming that we don't lose elements in the impact, but we did look into chemistry and what that would mean. And I think the biggest implication of chemistry is that it would form N2 out of nitrogen that's present, and N2 was not observed in the plume because it is extremely difficult to observe remotely. And so the nitrogen to carbon ratio is actually, that was observed by LCROSS, is actually a lower limit. And we did take that into account.